So we discussed about complex valued signals, and then we saw that they are important mainly because we use phasors, which are complex exponentials, to model the kind of signals that we encounter in electronic circuits, especially when we have capacitors and inductors. There is always a phase lag or lead in circuits, right? So in order to model this particular phenomena that we encounter in circuits, where when you apply a voltage and then see what happens at the output of the circuit in a capacitor or in an inductor or in a resistor where there are capacitors and inductors present in the circuit, there is a phase difference. And in order to analyze this phase difference and in order to design such circuits, we use phases to represent the kind of voltage signals and current signals that are passing through in this circuit. And that helps us to do this analysis mainly because the phases are nothing but the eigenfunctions of the integrator and differentiators. What are the eigenfunctions? It simply means that if you feed in some f of t to a block, and that block in this case is either an integrator or a differentiator, then the output is some constant times f of t. Okay, this is what we are seeing, and this, depending upon the integrator or a differentiator, it changes. For an integrator, it is something like 1 by j omega, and for a differentiator, it is j omega. So we feed in a phasor, the output is the phasor as such with some constant multiplier. So this is a very important property that becomes extremely useful in the analysis of circuits with capacitors and inductors. And this is the main reason we use phasor representation, simply because it reduces a lot of complexity in analyzing the circuit. And it tells us what happens to the phase, what happens to the lag or lead that is present, and what is the phase shift. And this helps simplifying in our complete analysis of the circuit. Okay, so that's the importance of phasors, and that's the need for using complex valued signals in systems. So we also saw that the phasors will have a magnitude and there is a phase. If the magnitude is 1, then we end up calling this as a complex sinusoid. A phasor is simply nothing but some r times e power j omega t, or in other words, you can write it as e power sigma plus j omega t. If sigma is 0, or in other words, r is 1, then what you get is a complex sinusoid. It's nothing but a sinusoid which has a magnitude 1, okay, and a complex representation given by cos omega t plus j sin omega t. And in this notation, we also saw that it is possible phasors can have negative frequency. Real valued signals really don't have any kind of the sign for the frequency, whereas phasors have what is called as the sign of the frequency, which is basically nothing but representing the direction in which the phasors rotate. Okay, the direction could be clockwise direction or it could be anti-clockwise direction. If it is anti-clockwise, we claim that the frequency is positive, and if it is clockwise, we claim that the frequency is negative. Okay, so this is the summary of phasors, and we also visualize phasors through two plots. Because real valued signal, there was just one value per time, so there was just one plot that is sufficient. At the moment we have complex valued signal, there is either the real part and the imaginary part. So what we need is one plot that shows the real part and the other plot which shows the imaginary plot. There is another way to represent or to visualize these complex valued signals, that is to see the magnitude and to see the phase separately. Okay, and what that we need to keep in mind while we are plotting the phase plot is that the phase wrapping is a phenomena that will occur during plotting of the phase plot, because the maximum value of the phases are going to be between plus pi and minus pi, or between 0 to 2 pi. Okay, so any value of phase which is beyond that has to be just wrapped back. So that is simply because you say that anything here in this two quadrants is something between 0 and pi. Anything in this quadrant is between 0 and minus pi. Okay, so if you have a value which is greater than pi, we will map that to something which is present in these two quadrants as a negative value. Okay. So hence there is phase wrapping that is present. So these are the phenomena that we need to be careful while plotting the phase plot of any complex valued signal. So this gives a nice summary of everything that we saw in phasors. Okay, so let's see an example. So in this example, what we have is a series RC circuit, which we already saw before, and hence we already have the voltage across the resistance and the capacitors from our analysis earlier. So in this case, we have an voltage source, okay, and the voltage source supplies an AC voltage, which is given by x of t, and then we are supposed to find out what is the voltage across the capacitor and the resistor. So we will use our phasor notation and then say that the input is actually a phasor, okay, and we'll find out the corresponding voltages across the resistor and capacitor, and then from that we'll find out what is the actual voltage across the resistor and capacitor in real life. But keep in mind, this is a phasor, which means there is a real part and an imaginary part. The actual signal x of t is basically nothing but the real part of this phasor. So we can write this phasor as v naught cos omega t plus j v naught sin omega t. And in our case, v naught is equal to 5 and omega is 2 pi times 50 radians per second, or you can also say that the frequency, the regular or the linear frequency, is 50 hertz. Okay, and we also have been given that the resistor has 2k ohms and the capacitor is 16 microfarad. So which means we can also find out what is RC omega. RC omega is 2 into 10 power 3 into 16 into 10 power minus 6 times 2 pi into 50. Okay. So we are going to make an approximation here. We'll say that 16 times 2 pi is approximately 100. Right? We are going to make an approximation. It is approximately 100. Or in other words, the approximation that we are making is 1 by 2 pi is approximately 0.16. Okay, that's the approximation that we are making. So with this approximation, we'll say that 2 into 10 power 3 times 10 power minus 6 into 10 power 2 into 50. Then we'll multiply this 50 with this 2 and then say that is 10 power 2. Okay, which gives us a very simple and straightforward 10 here. Okay, that's an easy number to work with. Okay, so which means that we can find out now what is VR of t. So VR of t, according to this equation, is V naught, which is 5 times 10 divided by square root of 101 into e power j omega t plus j5. And what is 5? So now what we have is tan phi is 1 by 10. So phi is tan inverse of 1 by 10. Okay. So this is some angle. So let's keep that as some phi. So the signal that we are looking for is roughly equal to, you can probably cancel this out, roughly it's 5 times, taking the real part of it, we'll say taking the real part of it, we have 5 times cos omega t, which is nothing but 2 pi 50 t plus phi. Phi is tan inverse of 1 by 10, which is roughly it will be about 10 degrees or something. Whereas the capacitance is given by a similar expression, V naught 5 into 1 by square root of 101 e power j omega t plus, once again we have the same expression here, which is so this minus pi by t. When you take the real component, what we have is, once again we have 0.5 roughly, okay, cos of 2 pi 50 t plus phi minus pi by 2, right? So this entire thing you can rewrite this entire expression could be rewritten as minus of pi by 2 minus 2 pi 50 t minus pi, and cos of minus theta is cos theta, and cos of 90 minus theta, that is pi by 2 minus theta, is sin theta, so which means this is 0.5 sine of 2 pi 50 plus, okay. So if we are trying to plot this, then what happens? The input signal is a cosine signal, right? Let's say this is x of t, sorry, and the output signal, as you can see, is still roughly across the resistor is 5, so which means here if it is 5 across the resistor, it's almost whatever is fed in the input, but then it has a phase shift. It comes with a phase shift of plus 5, so which means what happens, so when t is equal to 0, we are supposed to get the peak of cos, then when t is equal to 0, we'll get cos phi, which means that instead of starting at the peak, so here it's the so at t equal to 0, which is this point, we get the peak of the cosine function. So this is the peak, whereas when you are trying to plot PR of t, we'll start at somewhere where there is a phase shift. So the peak is somewhere on the negative time, okay, and this is minus pi. Okay. So there is a phase shift between what is fed as the input and then what we are seeing at the output of the resistor. And if we're trying to plot what is happening at the capacitor, it's even much different because it's a sine wave altogether. So it is a sine wave and it is at phi. So sine wave is supposed to start at 0, but then there is a phase difference phi. So it will, instead of starting at 0, it will start at some phi like this. Okay. And one thing to notice, this amplitude is 0.5 minus 0.5, whereas these two are 5 and minus 5. So this tells us that this phase difference between the input and output exists if you are going to measure the voltage across the resistor or a capacitor, and then you can easily compute that using these phasors. So you don't have to go and solve very complex differential equations. All you have to do is just take a look at these phasors, plug in there, and then you can easily compute the voltage and resistors. So the phasor analysis helps us to understand the phase difference between input and output and then easily evaluate them and analyze them. Okay, so now that we have understood the different kinds of signals, real valued signals, complex valued signals, and then some standard signals such as step function and rectangular functions and so on, let's see the properties of signals next.